As I said, the goal of this class is so that you know how to use LP as like a tool of thinking, right? And there are two ways in that, like when we don't use LP as a black box, to use it as a way of thinking. Well, one is to just prove some theorem, like nothing algorithmic, like prove some cool theorem. And next is to use it for designing algorithm. Today we're gonna see how to use it for proving theorems, in particular the Maxwell-Minkowski theorem, how to derive that from LP duality. And next week, you'll see how to use LP for designing algorithm. Okay, so let me recap a bit about Maxwell-Minkowski. We need to kind of recall the concept of flow. Yeah. So flow, there are two constraints about this. Can you recall what are the two constraints? Yeah, Maxim?
It shouldn't, whatever the flow shouldn't exceed the capacity. And also, it should be the same as without.
Exactly, good. Thanks, Maxim. So we need like a capacity constraint, that's one. Another one is flow conservation, right? That's what it means to be a flow. Okay, to be a ST flow. Okay, so now let's say that I look at some ST flow. And let's say that C is some cycle, right? It's a cycle in a graph, and I represent it as like a 0, 1, like a vector on each edge. Yeah, put 0 or 1. Just choose each edge, whether you choose it or not. For each edge, whether you choose it or not. So cycle is like a subset of edge. Okay. A path can be represented as a vector like this too. And so here's some quiz, like a quick question. I will ask is the following is an ST flow? And if so, what is its value? Okay. So the first is F. If you add a cycle into F, is it still an ST flow? Who say yes?
Yeah.
Who say no? Is it understandable question? Okay.
Adding a cycle into a flow?
Yeah.
Is still a flow.
Yeah, just add a cycle into the flow. Is it yes or no? Yes, yeah, it is, yeah. Because, well, oh no, it might not be. Okay. So first, if you ask about flow conservation, then yes, right? Because every edge of cycle, every node in a cycle have the same in and out flow, in and out value. So flow conservation would be satisfied, right? But it might violate the capacity constraint.
Wait, how could it? Because you're just adding more edges to the graph, right?
Oh no, I mean
adding it to the path.
Adding it to the flow.
Oh, okay.
So, for example, the flow might be like this, and then let's say I have maybe just this thing too, right? But let's say everything is 1, and I have the flow like this. But if I add another thing here of 1, well, this is violated. Make sense?
Yeah.
Okay.
But you're adding.
So if I add 1, 1,
Yeah.
1, 1 here, the value here would be 2.
Yes.
But let's say the capacity here is 1.
Yes.
So it used to be, the flow used to respect the capacity without the cycle here.
Yes.
But now it doesn't after adding this.
What are you adding in more
I don't. Let's say I don't add the capacity to the graph. I just add this value
Yeah.
to the flow.
Yeah.
Then it
Then
will.
it does work. Yeah.
Yeah.
Okay.
Okay. Good. But okay, what if like the cycle is a subset of the flow? That is, let's say you have some feasible flow, and this cycle is like a subset of this flow, and you remove the cycle. Is this the ST flow?
Maybe not.
Why not?
There could be. It could break all paths between S and T if there's only like. Is that possible? Or
It might break some path, but actually it's gonna still be a flow, actually. Why is that? Well, first, like the flow conservation is true. Just because like you used to have something that is flow conserved and you subtract something that is flow conserved, it still be, the flow conservation is true.
that's good.
And capacity constraint will be true as well in this case, because you only reduce the value of the flow. And like you reduce something that is what's there, so it's still valid. Yeah.
What if you use your example and the capacity was 2 on the top, so it would be a valid flow? If you
Yes.
take out the cycle, you can't really reach ST then.
Okay, let's see the example. Good. So let's say that the capacity here is like, maybe let me write it again like this. Shoop, shoop, shoop. And then I have kind of, I add another thing like this, right? Okay. So when you have this double edge, you should think of it as like value is 2 here. And maybe there are 2 edges like this. Okay. And okay, well, if I, like, you can see that if I just remove the purple thing, then you get the flow. Yeah. Or if you, for example, think that, like in the beginning, actually, like these 2 cancel and it's 0. Like before I remove the cycle, it was 0. And if I subtract the cycle, then it would go in the flow would go in this direction. So it's still good. But it doesn't satisfy this case because here I really want that like the cycle is actually like a subset of the flow. Yeah.
And so it's true to say that there will be a flow, but it might not necessarily be the same value flow, right? It might be lower if you take out the cycle.
You will have the same value, it turns out. Why? Yeah, this is my, like, it is a valid flow. Why its value must be the same?
The cycle, like it always cancels itself out.
Exactly. Like the value is just the net flow going out of S. If you subtract the cycle, no matter how much, the net flow stay the same at S, at the source. Make sense? Okay, good. Now, okay, I ask the same question. Let's say P is the ST path. Okay. Now you add ST path add the path into the flow. Is it always a flow?
Like if F already included P, like if F, like you might exceed capacity.
Yeah,
F
again,
might be-
you
like,
might
P might
exceed
already in
capacity.
Yeah.
Yeah. The flow conservation still hold because we only care about the thing that is not S and T. Like we only care about flow conservation that not like at every place except S and T. And at every place except S and T, flow conservation for the path is true. So flow conservation is fine for this, but you might again exceed the capacity. What about this? Subtract. Yeah.
No, if P is a blocking path.
No, it's P is a blocking path. Why?
If P is a blocking path, then
What is blocking path, by the way? Yeah.
where it's a path, I think, where all of the edges are saturated in it.
Okay. Uh-huh.
Like every path from every possible path from S to T has to take at least one edge from P.
Okay.
And so if every path has to go through an edge in P and you take P out, then you can't get from S to T.
Okay. It could be the case that like once you subtract the path, then your flow value is 0. That can happen. But flow with value 0 is still the flow, actually. It's still a flow.
Okay.
So the answer here is that it's still true. It's still a flow. And the only thing you need to check again is just flow conservation and capacity constraint. Capacity constraint is true because you just subtract things from the flow. You only reduce. Flow conservation, well, true as well because you subtract a path whose the value in and out value on a path is are the same at every node except at S and T. Okay. What's the value of this new flow?
Less than or equal to what it used to be.
Yeah. By what? It's going to be less, but by what?
Like however much is going through P.
Right. But here I really subtract 1.
Oh,
So
yeah.
it's just reduced by 1. Yeah. Okay. Good. Okay.
Sorry, I have a question.
Yeah.
Could you draw for a graph where it's like so there's S and then S goes branches 2 ways and then let's say they come back together and then it's just a straight path to T.
Good.
If you take out P, there's no path, so
Like this.
something
Yeah.
like that.
Good.
And then you take out P, which is we'll say the bottom part of that.
Yeah.
And then you're just left with the top part and that's still a valid flow.
Well, it depends. If the flow, change the color. Is the flow like this, or also have something here too?
Yeah.
Then the value here must be 2, right? If this is 1. Okay. And if you remove one path here,
Yeah.
then what you get at the end is 1, 1, and 1.
Okay, so we're saying that's 2 different. Okay, so we're not subtracting the edges themselves, we're subtracting the capacity from the edges.
Yeah.
Okay.
Yeah. Sorry, that's what I mean. This is by here. I really mean I reduce the value, the flow value on each edge, on each of these edge on the cycle or on the path. Yeah. Right. Yeah. So here I mean you just reduce one here, and what you get is still the flow. Okay. Last thing is just, let's say I asked about this, yeah, and P is also a subset of a path of a flow. Okay. In this case, if P is not an ST path, let's say it starts from some other place that is not S, or end at some other place that's not T. If you subtract this, now it's not gonna be a flow because the constraint that is violated is flow conservation, right? If it start at a node V, and it's a VT path. After subtract by P, then at V, the flow will not be conserved. Okay, so with this in mind, like it will help you to understand like flow decomposition a bit more. What I want to say is this. It means that for any flow f, you can decompose it into like a set of st paths and cycles. And we have actually seen this before, like in like previous class, where you have flow and when you try to extract the disjoint path from the flow. You remember that we try to do DFS from the source until it reaches the sink. If it doesn't reach a sink but it finds a cycle, then you subtract the cycle from that flow and repeat. So if you just do that DFS, what you get is like you either get a path, st path, or once you find a cycle, you just subtract the cycle. Keep doing that. It means that like you can just decompose any flow into like a sum of path, st path, and you scale it by like some value xp for each path p, or you get like a sum of cycle, and each cycle you scale it by some value xc. Question about this? Good. Okay. And note that like this decomposition might not be unique, because when you do DFS, for example, you might find different set of paths. Yeah. And by the way, like note again that cycle here that add up to your flow do not contribute to the flow value at all. Only the path here that contribute to the flow value. So if you consider another flow, f prime here, where I just collect all the path part of f, right, and I neglect all the cycle part of f, the flow value f prime, the value of flow f prime here, it's just going to be the same, right? Because this is just like some set of cycle. It contributes zero value. Okay. So let me give some let's see some example of flow decomposition that decompose into path and cycle from here. Okay. Like I might start with this path and I get 5 here, right? And now maybe this one, I go here, this path, and then I just take 2, value 2. Yeah. Good. All right. And then there could be like another path like this of value 2. Okay. And then maybe I can have a cycle like this too. So like adding this path with value 5, path with value 2, this purple path with value 2, and cycle with value 1, just give you this flow. Okay. Is this max flow, by the way?
No, I think you can put one more unit of, oh wait. No, I think it is a max flow.
No, you can put one more unit through.
Yeah. How?
You put it through the 5-6 edge, the 1-1 edge, 3-3 edge, and then
Oh, yeah.
Yeah,
Taking
like,
out the cycle.
like go like this, and then like go like this, like a side, cancel this guy basically, and then go here. Am I right?
isn't the edge pointing the other direction?
Yeah, but like I kind of I have sent flow in this direction,
Oh,
so I could have cancel it
yeah.
and then come here. Yeah. Okay. Anyway, yeah. But it's just some flow, and for any flow you can decompose it into path and cycle. This one you can this is a max flow, by the way, because here, right, it's saturated, and you can decompose it into path too. One example is like this one, put it 20 here, and then here put it 20. Now this guy have like 5 more capacity, and I can just go through this and put 5, and like there are many paths, yeah, and so on. Anyway, you get an idea. Yeah. Okay, good. Just to recall what is flow and path decomposition. Okay, so now let's go to like some LP formulation of max flow. This is gonna be different LP formulation. Last time we saw some LP formulation for max flow, how to capture max flow with LP. I'm gonna do something different. Okay. So my point is actually there are several reasonable ways to formulate the same problem as an LP. So you see another formulation today. So let's say that I start with the variables, where like I have a set P here. P is now the set of all ST paths. P is not just one single path, right? P is a set of all ST paths. There are exponentially many. For example, like if the graph is like this, yeah. From S to T, there can be like exponentially many ST paths. You can choose to go up, go up or down or up, and yeah, exponentially many. Okay. So I just introduced like exponentially many variables, okay, where like I have x of in R to the P. So I have like a xp for each path P. I have some value xp, which is like some number. Yeah. And xp here will represent the amount of flow that's sent along the path P. And now my objective is I want to maximize the total value on all ST paths. Okay. Note again, when you look at flow, and if you care about value of the flow, you just care about ST path. You don't care about cycle, right? So it kind of makes sense to just try to optimize this thing. Okay. And now we need to put some constraint to make this capture max flow. What should be the constraint? To do that for all edge. E. What should I write? What constraint should I write? What linear constraint should I write? Like it should be something less than the capacity of E. What is this part?
Like the sum of either you could say like outflows from like vertices that go to that edge, or like inflows.
Right, but I kind of want to use only this variable, like xp variable.
the value of xp should be less than or equal to the capacity of every edge along its path.
Like you mean like this, like x
Never mind.
xp at most this for all e in p, something like this.
Yeah, but it could be that multiple.
Yeah, there can be multiple paths.
Yeah.
So this is like you need this, but it's not enough.
So summation over all xp that include that like go through E needs to be less than or equal to capacity.
Exactly. P such that like P contains E. Right? Just really like a sum over all paths that contain E. Look at the value of those paths. The total flow going through that should be at most the capacity. Yeah. That's it. Yeah. That's the constraint. Yeah. And this actually just already capture what max flow is. Right? And to see this, like you use the fact that you know that all you care about flow is just like flow. You now think of it as like a just combination of ST paths. So it's just about now packing as many ST paths as possible. Like you want to maximize the value on ST path. As long as you pack this and it respects the capacity on every edge.
And we don't need to worry about conservation because for all of the XP, the flow is just remaining the same.
Exactly. Yeah. The conservation is now implicit by the fact that we like take the variable is on each path, on each ST path. Yeah. Okay. So this is now just like some nice and simple, simple to write LP, although it's a huge LP because there are exponentially many variables. But like we write it in a succinct way. Okay, but let's try to derive dual. Okay, and you like I suggest you look at the cheat sheet, but we're gonna do it together today. Okay, so the primal is this. It's just like you maximize this with this capacity. Okay. And how to derive dual? Well, the first thing is just you're gonna create you create a variable, the dual variable for each primal constraint. The constraint for each primal constraint, it corresponds to each edge. So you create a variable lambda e for each edge e. Okay. And lambda will be at least 0 because the constraint here is at most constraint. So you put like at least 0 here. Next, note that like okay, the way you think of dual, right, is to like basically you try to come up with the best upper bound for the LP, right? So you come up with like this thing is like what is the best linear combination to put to each constraint so that you get the best upper bound. So you think like you put like you multiply this dual variable to each of the constraint here and try to get the best upper bound. And the upper bound that you get is just when you multiply this thing to the right hand side, this is the upper bound that you get. And we want to basically get the best upper bound, so we want to minimize this thing. Okay. All right. But our upper bound needs to be a valid upper bound, meaning that when you look at the left-hand side and you sum them up here, this left-hand side is this one. It needs to be a valid upper bound, so what should this satisfy? This whole thing needs to dominate the objective here. Right? So that is a valid upper bound. So you want that this whole thing is at least x this thing, yeah, xp for all p in the ST path. Make sense? This is what we want. Okay, and for this to be true, it means that like for every coefficient of xp, like the coefficient of xp on the left hand side here need to be more than the coefficient of xp here. So it just means that, it just means this, right? For every xp, that is for each st path p, the coefficient on this side need to be more than this side. So that it is just mean that the sum of lambda e when e is in p is at least 1. Okay. All right. Yeah, that's like how you derive the dual. But this is a bit when I in real life, like when you try to do it, you don't really, at least I don't really think about trying to obtain the upper bound explicitly. I just kind of use a cheat sheet. How to do that? Like let's try. Let me try to show you how I do it, right? Again, like I have we have this primal. You have this primal LP, and okay, this is like this is a constraint. There is constraint for each edge. So I know now that like I need to have variable for each edge. For each edge. So I just say that this is lambda e for each edge e. So lambda is just and each this constraint is at most constraint, so lambda need to be at least 0. I just do this, right? And now what I'm gonna do next is just say that okay, this is max, so I put min. What should be the objective? Well, I just look at the right hand side of this thing. So it's gonna be sum of and I just multiply this to this. Lambda e ce lambda e. And sum over all constraint here. So which is just sum over every edge. So sum over every edge here. Okay. So that's the objective. What about the constraint? Well, I just said that okay. Well, I kind of just look at maybe the best way is to see like how many constraints do I have? Well, because primal dual constraint correspond to primal variables. So I know that what are the variable set of primal is just a set of all paths. So I just know that like the constraint is like for each st path p, and now I need to write the constraint. Okay. The constraint is gonna be what? It's gonna be like I have for each path p here, I need to know the right hand side and the left hand side of the constraint. The right hand side, I just look at the objective here. Like for each path p, the coefficient here is 1, so I put 1. And what about the left hand side? Well, I just need to ask like how many, like, okay. Let me just write it down. It's gonna be lambda e for all e in p. Why is that? It's like I just need to ask for each fixed path p, when you sum overall constraint here, like for every edge, you have like, okay, you ask like when xp appears in each of the constraint, well, it will appear for the constraint that e is in that path. So I just like I just put it like yeah, like the constraint, the primal constraint that xp appears is the constraint where the edge is in that path. So so I just sum over all edge that is in that path. Okay. Anyway, this is just how I do it. Okay. Okay. And you can have a look. Yeah. But like how do you do it in you can try to do it step by step and try to find like some shortcut on your own. Yeah. Right. Okay. Anyway, we have now come up with the dual LP. It's just some LP. Okay. And usually, like whenever you derive at a dual, it's really useful to interpret what this dual like represent. Like it's like a sum of the LP is an optimization problem. What does this optimize? That's the question. So let's try to interpret this. Okay. Let's stare at this LP. Okay. And my first observation is that there's no good reason to ever choose lambda e to be more than 1. I claim that there always exists an optimal solution where for every HE, lambda e is at most 1. Do you see why? Blake?
Your constraint on the bottom, it says that the sum of all the lambdas need to be 1, and you're
At least 1, yeah.
but you're also minimizing
Exactly.
lambdas in the objective function with a weight, but still.
Exactly, yeah. So we want to minimize things, but like but here you only need things to be as big as 1. So if there is exists some edge e where lambda is more than 1, like let's say it's 2. If you just set that, like ignore every other lambda e prime, every other variable, just look at that lambda e. If it's 2, just set it to be 1. Everything here will be still satisfied. And your objective can only get better.
you explain, so lambda e, is that just the constraint variable, or does that have some like significance in the context of the problem?
Lambda is this variable, and like we have a constraint for every path. How to like right now we are actually in the process of interpret what should lambda e means. Yeah. Okay. Okay, but my point is that like you actually can assume now that lambda e should be between 0 and 1. Okay, so let's assume this. Okay. And now like let's try to interpret this a bit further, right? So what does this thing solve? What does it optimize? Okay. Now one of the useful steps to interpret any LP, right, is to force the variable to be integral, because it's easier for human to think integrally and then interpret it again. Okay, so let's do that, right? So I just force the variable to be integral, and it's now just 0, 1. So when you force it like this, it's like for each edge, whether you choose it or not, right? And good. And I give you 1 minute to think, what is this? What is this problem? You need that for every edge, for every path from S to T. When you go along the path, there must be at least one edge that you choose, right? Because this is just 0, 1. So when you look at all the edge along the path, there must be at least one edge that you choose. That's what it means here. And you want to minimize this thing. What do you think is this problem? Yeah.
Is it minimizing the fraction of capacity that you're going through for each edge? Like lambda e denotes the fraction of the capacity of that edge that you're using?
Yeah, but right now it's just 0, 1, so it's not really fraction, right? Like if let's say like if you choose lambda e to be 1, then you pay like the capacity of that edge.
So then just like for each edge, whether or not you're going through it in your path, or I guess whether or not you're using it in your flow.
Okay. Yeah, I give you some more.
Is this reminiscent of min cut? Because you essentially might get the minimal amount of cost that you like use, but you still have like the two different.
Yeah, yeah. Say again, like why you think it's close to min cut? Yeah.
Because you're trying to minimize the number of like costs that you have between the two different sets using the objective, but you still want the flow from the constraint to like still have at least one path.
Right. Yeah, good. I think that's a good direction, good intuition. And anyone wants to say more? Yeah.
I have a question. So we said that there could be an exponential amount of paths. So I'm a little bit confused about this constraint. If there's an exponential amount of paths, that means we're like choosing an exponential amount of lambdas to be 1. So we're like choosing
No, like
that many edges.
the number of variables here is just number of edges.
Oh, okay. Okay.
But there are many paths. Yeah.
Okay.
So let's see the example, right? Let's say that the graph is like this. Right. S and T. And let's say the capacity is all 1. what would be the best solution of lambda? Yeah,
The middle one.
the middle one, right? Yeah, because like, and even if I add this edge here, the solution is still like a middle one. Because like once you choose this edge, like every path from S to T must go through this edge. So this is true, and you can just choose one edge. So it's the best thing. If you don't choose any edge, you like this will not be true. So this is the best solution, and actually like actually this is exactly min cut problem, ST min cut problem, because for ST min cut, right? Like basically you choose whether an edge should be in the cut or not in the cut, and you want to minimize the total capacity of edges that you choose. And what does it mean to be min cut? Is a thing such that once you remove it, there is no ST path left, which is the same thing as saying that for every ST path, it must go through at least one edge in the cut. So from just by deriving dual, look and try to interpret it. You can see that it's just a min cut problem. Okay, but it's not really the same problem. It's because we force integral variables. But we know what? We know that when you don't force integrality, and I call this fractional min cut, which is a dual that we have. The objective of this guy is going to be at most the objective of this. Why? Because like it's the same thing, the same constraint, the same objective, except that the search space of this is like more relaxed. So we try to minimize in the bigger search space. Okay. All right. So what do we have so far? We have that min max flow must have the same value as fractional min cut, and is at most min cut. Why do we have this inequality?
Strong duality.
Strong duality. We assume this, and we're gonna just use it. This is just because of strong duality. We want to prove that this part, they are the same too, so that we can, if true, then we would prove min cos max flow theorem. Right now we just have one direction, but like next I'm gonna show you that they are actually the same. Okay. That is, fractional min cut is the same as min cut. And by the way, this is a special property of min cut. That is, when it's not true for any LP, it's just true for the LP for min cut. But you see that, like now to prove this max flow min cut theorem, now it's not about coming up with like some algorithm, no Ford-Fulkerson algorithm. It's now kind of about trying to show that when you have an LP, they have like it's the same. The LP without integrality constraint is the same as the one with integrality constraint. It's just now about that. Yeah. Okay. So let me try to prove this, that they are actually the same. Okay. So I want to prove that min cut actually is at most fractional min cut. Okay. So that is, what do we want to show? We want to show that, suppose that I give you any like fractional ST cut, like lambda here, and the total value of that like the objective is this much. It suffices now to show that the exists integral st cut, which is the set of edges, such that the capacity of this cut is at most a value of fractional 1. If I can show this, you agree that we are done. Right? Okay. So let's try to look at the fractional cut and interpret it even a bit. Right? Fractional cuts, lambda here is like just assign some fractional value on each edge. What does it satisfy? You think of it as like a lambda e as an edge weight at each edge e. And what it satisfies is that the distance from S to T will be at least 1.
Yep.
Why? Well, you have this thing, right? For every path here, the total length is at least 1. So it means that the shortest path from S to T is at least 1. So lambda e is just the weight assignment such that the distance from S to T is 1. Okay. Now let me try to define some cut, right? Suppose that I fix any value like threshold tau. And for any threshold tau, I can define a cut C tau to contain all edges crossing the threshold. What I mean is that I'm gonna put UV to the cut if the distance of U is less than tau, like less than the threshold, but V cross the threshold. But V kind of cross the threshold. The distance of V cross it is more than tau. For example, if my tau is 0.8, then this would be the cut. It would be this cut because this is like a kind of 0.75 here, and it's this one, and it's this one. So if tau is kind of close to 0, then C tau would be close to S. The further I go, like it's gonna closer to T. Make sense? Like C tau is like some set of edges that kind of start on something that's close to S, and when once tau grows, it's close to T. And you should agree that like a C tau must be an ST cut, like integral one. Why is that? Because like once you remove for any tau, once you remove C tau, there cannot be any like a ST path left. Make sense? Because like to go from S to T, kind of you need to like increase the distance from 0 to 1, but like but C tau will basically remove all the edges that cross some distance threshold. So once you remove C tau, then there is no path. So C tau is a ST cut, integral one. Okay. So and my goal is this. Forget this for a moment. My goal is that I will show you that there exists tau such that the capacity of C tau is at most the fractional value of the min cut. So basically we are done here. If I can find you a tau such that this is true, then we are done. Now, how to find such a tau? I claim that just choose a random one. Like I just sampled a random tau from 0 to 1, and I claim that the expected capacity of the cut C tau when tau is random is at most this. So basically on average, the capacity of C tau is at most this. So there must exist tau such that this is true.
Yeah.
Okay. So now I just need to prove the lemma here. Okay. Question up to this point? Yeah.
What? Oh, sorry, I wasn't.
Okay. Are you with me? It's good?
You explain again quickly why C tau is an integer ST cut?
For sure. So, like, oh, you know that, like, from S to T, like right now the distance from S to T, the distance here is at least 1. Like there is no path of length less than 1. Do you still agree? I can try to tell you why this is true, but you agree with this?
Yeah.
Okay. And now, so it means that like to go from S to T, like the total length of the path is at least 1 for any path. But now, what do? We basically cut, like we kind of find like some threshold tau here. And for any node that cross, for any edge where everyone here has distance less than tau and everyone here has distance greater than tau, I just cut all the edges that cross this threshold. In particular, the path. There will be some edge on the path that I will cut. So this is true for every path, that I just gonna cut some edge on the path. So there's no path from S to T left.
Mm-hmm.
Okay. More question. Okay, so we're gonna prove this now. Okay, so it's just about like computing the expected value of the capacity of this random cut, like when tau is random. Well, we just need to compute expected value of the cut, so just write down what it means by expected value of the capacity. Well, it's just like, this is just the expected value of this capacity is just like the sum over all edge, the capacity of that edge times the probability that you pick that edge. Okay. Just use linearity of expectation and so on, right? Okay, so now we just need to analyze what's the probability that E will be cut when you choose tau randomly. Okay. So I claim that the probability that E, like an edge UV is cut, is exactly this thing. How to see this? Well, you know that like S is here, T is here, and U and V is somewhere like I just write like an interval from 0 to 1, and I put U into this place at the distance of U from S to T. And V is just I put V here at the position of distance from S to V. Oh. And when will an edge UV be cut? If I choose like the threshold here, if I choose the threshold here, then it will not be cut. If here, it will not be cut. But if it's here, then it will be cut. Okay. So CU, like UV is cut if tau is in this interval. And like, this is like the interval of size 1. And this is an interval of this size. What's the probability that we pick something in the red interval? Well, It's just the length of this interval. Okay. But this is at most the length of an edge from U, the length of an edge from U to V. Why is that?
It's just it's just the distance.
Yeah, it has to cut across an edge.
So, this is a distance. This is a distance based on lambda, right?
Yeah.
And why this is true is just triangle inequality. You have that, you have S, you have U, you have V. So the distance from S to V is at most the distance from S to U plus, if this is A, B, C, then A is at most B plus C. So you have distance from to S to V is at most distance from to U plus the weight from U to V. Okay. And so we are done. We get that this is just at most lambda E. So this is at most this. Okay. So what did we get so far? It means that given any fractional cut, you can find an integral cut with the same value. So fractional mean cut is the same as integral mean cut. Now it just proves, gives you very different proof that max flow and mean cut are the same. Okay. And this is actually happening, so this is just some example how to use LP to prove some combinatorics, right? And I just give you this example because you have at least have intuition about max flow and mean cut. You have seen that. But you can use it to prove so many other things. Basically, whenever you come up with any problem that can be captured with LP, you can just try to look at the dual, interpret that dual. What is this problem? And now you will basically get some connection between two very different problems. And if it's the case mean cut here, where the fractional value and the integral value are the same, then you get a new theorem. That's it. There's so many proofs like this in literature. And if you want to learn more about this, I recommend the course by Chandra. Combinatorial optimization, Chandra Chekuri. I think this one. Right. And I think he has video lecture too. Video. I don't. Anyway, yeah. I gonna put it in the version, in the slides after this class. But there is some a theory which says that if you look at this LP and you see immediately that if it satisfies some constraint, then you know that the fractional value, the fractional version and integral version must be the same. And there is a theory for this. And once you have this theory, you get a bunch of other combinatorics theorem. Yeah. So it's a really cool thing. Okay. Let me talk about. By the way, I also put my like another write-up on deriving dual. Like so we see how to derive a dual for one formulation of MaxFlow. But let's try, like here I show like how to derive dual of our original LP formulation of MaxFlow. You're gonna get different dual. Start with different LP, although it's the same problem, you get different dual. So I just try to do this step by step, and you can read up, and you do some of this in the homework for different problem. Okay. And in the next class, we will talk about approximation algorithm using LP. But let me like start by recalling what's the concept of approximation algorithm. Easy going for this class. And next class, let's try to solve it using LP. I think if you have taken like a 376, you have seen what is approximation algorithms, but I'm gonna just go through it anyway. Okay. So, what is it? What is approximation algorithm? Well, if you start with like any problem that is optimization problem like max flow, min cut, max cut, and so on, right? You look at this kind of problem, and let's say that there is an algorithm for the problem, right? Then I can denote, given an input I denote like out of I to be the value that is achieved by the algorithm, and opt of I to be the optimal solution given this input I. Okay. We say that the algorithm ALG is an alpha approximation algorithm for P if basically the solution of the algorithm is basically as good as the optimal solution up to factor alpha. If it's a minimization problem, then algorithm is not too big compared to opt up to factor alpha. And if it's maximization problem, then the solution of algorithm is not too small compared to the optimal solution. You can talk about this concept for randomized algorithm as well, where you just replace this value of the algorithm by the expected value of what the algorithm returns. Okay. You can also say that, okay, this thing holds with some probability. Okay. Just like a natural concept. Okay. And this alpha is just is what we call approximation ratio of the algorithm. If alpha is 1, then it's exact. It's just as good as the optimal one. If alpha is close to 1, then this is what we want. It can be 2, it can be 10, it can be log n, can grow with n too, grow with f. Okay. Well, why don't we compute exact solution? Well, because some problems are NP hard, right? And sometimes even if it's not NP hard, like we don't know how to compute exact algorithm really fast, like linear time or sublinear time. Once you really care about running time, even if it's a problem in P, it's still like it makes sense totally to look at approximation algorithm. And we have local expert that just focus on approximation algorithm here, your advisor too. And yeah, so let's look at like a really simple first approximation algorithm for vertex cover. Okay. So recall that vertex cover of a graph is a vertex set S such that every edge at least has one endpoint in S. Like this. If this is a graph, then this set is the vertex cover because there is no edge like this. Nothing like this. Yeah. Okay. So the goal that we want to do now is like given a graph, we want to find vertex cover of minimum size. Okay, so and here is like a super simple algorithm. Compute a maximum matching M like this thing. You remember what is maximum matching? Just like a like a set of disjoint edges such that you cannot add another edge into it to make it still matching. So you just can compute this greedily in linear time, just go through each edge. So this is just a maximum matching. It's not maximum, but maximal. And once you look at this maximum matching, just look at the vertices inside the matching and return that set. Okay. So it's a linear time algorithm. Like here you compute maximum matching, and then you return this set. Okay, that's the algorithm I claim. And do you see why S must be a vertex cover?
I mean, by looking at the graph, or by like.
Yeah, give me the proof now. Why this algorithm must return a vertex cover? Yeah.
Because if it didn't, it would just add that edge into our maximal set. Right?
Exactly.
Yeah.
If there is an edge not covered by this set, it means that you could have added edge into dual matching. But our matching was maximal, so that cannot happen. Okay, so it is a vertex cover. Okay. And I claim that it is a true approximation. Why? Well, from the description here, you have that the set S that you return is of size 2 times M, where M is the matching size. If there are 3 matching edges here, then your solution size is 6. But I claim that the optimal solution must have size at least M. But the reason is why is this. For every edge in the matching, right? For every purple edge here, we know for sure that this edge must be covered. Like every edge must be covered, in particular the matching, the edge in the matching must be covered too. So if U and V is in the matching, then either U or V must be chosen in any optimal solution.
Yeah.
So for each matching edge, it must contribute 1 to the optimal solution. So the optimal solution have size at least M. Well, the optimal solution is at least M. Your solution is at most 2M. So you get that you're as good as optimal solution up to a factor of 2. Make sense?
Wait, sorry.
Yeah.
Why is opt at least M? Because what if you had one vertex that connected to every edge? Then wouldn't opt be just 1, even if there was like 10 edges?
No, like if you have an edge here, UV, and like this guy connects to everyone, you still know that like you know that like either U or V must be chosen anyway. Yeah. In this case, like the size of if the graph is like this, then the size of maximal matching is 1, by the way. You see?
Yeah, so what I'm saying, cardinality, is M the number of edges?
Yeah, this is the number of edges.
Isn't, so opt is just one, and there's,
Yeah.
so isn't opt less than M?
M in this case, if in this graph, op is 1.
Yeah.
And what you will do is to choose two nodes. So your solution is of size 2. Right? Because once you choose this matching, then you cannot add any other.
Yes, no, so I agree with that. My point is, I'm disputing the opt G greater than or equal to cardinality of M. Right, because what? Because isn't opt 1, but M is like 8?
No, M is 1.
Oh, M, so M is the cardinality of edges in the maximal matching set.
Yeah,
Okay.
M is the number of edges in the matching, in the maximal matching. Okay. Good. Question about this algorithm? That is give you a two approximation. Yep.
I think now I'm kind of running into the same thing. So let's say you have a graph that's like, it's just one line and it's 3 edges, like an approximation, like the greedy algorithm could pick the 2 edges on the side so that the cardinality of M is 2, but the optimal solution would just be the edge in the middle.
It's like this.
Yes, that's an example where you could like pick like
Yeah, you could just pick like everything.
Yeah,
Yeah.
like the 2 edges on the side
Yeah.
as opposed to the edge in the middle. But in that case, wouldn't the inequality be the opposite where opt of G is like half the size of M? Do you know what I'm saying? I think
So
I have a misunderstanding.
maybe I need to like maybe I need to make it clear. This is like the number of edges in M, right?
Mm-hmm.
Okay. So your matching can be like this, right? And in this case, your solution would be like of size 4. Okay. But the matching size here is 2. You agree? Like the
Oh,
matching
I see.
is just 2 edges.
Opt G is vertices.
Yeah.
Okay, that's where I thought opt was choosing the edges. Okay,
Right.
that makes sense.
An optimal solution maybe just choose one node here and one node here. Op is at least 2, which is at least M here. Okay. More questions? Okay. Good. So this is just like some ad hoc approximation algorithm. And by the way, like this gives you 2 approximation, but it turns out that can we hope for like a better than 2? Well, if you can do it, then you will reveal some conjecture. But this conjecture is called unique game conjecture, and no one knows really like whether it's true or not. Some people believe it, some people don't. But if you believe that P is not the same as NP, at least you cannot beat like root 2, which is like 1.4. Like it's like this hardness of approximation is like a deep area, and Uyong is like the expert here. But yeah, like okay. Next time we're gonna see like how to solve a bunch of problems approximately using LP. Yeah. And before we leave, this is a quiz. If a graph is a tree, why can you solve this problem exactly? Yeah, you can think about it. Yeah. Okay, yeah, that's it for today. See you next time.